I want to keep this this discussion interactive. So I'm going to start it off with like a question, right? So in your opinion, how does a computer work? So I want to keep this like maybe a couple minutes, just throw some ideas. Like if you were to try to explain to somebody, what is a computer? How does it work? What would be the first first bullet points that might come to mind?
Well, you feed in a set of instructions and it tries to execute them.
Feed in instructions, it tries to execute them. All right. Anything else?
0 and 1.
0, 1, 1. Okay, 0, 1, 0, 1s. Okay. So somehow there's a mapping of instructions and inputs that are encoded as 0, 1, 0, 1s, and it executes them. And so there's also this keyword execute in it too. Maybe I'll follow up that with a question as well. So what are some really fundamental, unshakable assumptions that we make now about what computers are made of, how they work?
Well, they're made out of electric circuits.
Electric circuits. Mm-hmm.
Chips.
Integrated circuits, yep, chips. I would say also the 0, 1, 0, 1 binary abstraction was also very much a fundamental assumption that we had before.
Yeah.
And I think one thing I'd like to particularly draw attention to is also there's a kind of discrete time assumption too. So that's also a kind of important abstraction that we make. So here's a kind of slide of a broader picture of computing in general, right? So here I'm listing some important areas, right? So we have general purpose computation that we want to tackle, but increasingly some of the most interesting areas in computer science are in modeling really difficult phenomena like quantum chemistry, fluid dynamics, or understanding how the mind works and performing high dimensional optimization. And so we've got the basic type of computers, you know, von Neumann architecture, stored program, CPU interfacing with a memory hierarchy to tackle the general purpose computation. We're starting to also look at, different physical processes that can be useful for computing. So here I'm starting to draw an axis here. So we have digital encodings with discrete variables on one end and analog encodings on the other. And as we explore this kind of dimension, people are already and even potentially bringing to market computers that are based off of analog variables, right? So they have these analog signal-based, memristor-based neuromorphic chips where you create an analog electronic circuit that implements a neural network, and you can train and do inference on that just as you would in software. And for my PhD dissertation, I worked on a team at Columbia where we built these analog electronic circuits whose behavior was described by an ODE, differential equation. And we used that ODE in the way that analog computers of the 1950s were used to solve basic ODEs. And we kind of brought some of those ideas to current problems. So now, in my research now, and in a really important area in computer engineering, people are also exploring an additional dimension, which is the encoding of variables in classical valued variables versus quantum valued variables that follow quantum dynamics. And so here is the main topic of our talk today, which is people are starting to investigate building computers that have data encoded in delicate quantum states whose statistics follow quantum mechanical behavior. And they're using that in a couple different styles to tackle problems in simulating quantum physics and for solving high dimensional optimization problems. All right, so that was kind of a lead in to a introduction to what quantum computing is. And I just want to remind, I welcome questions and comments all throughout the talk, right? It's more important that I want this session to be interactive than to get through the material. So feel free to interrupt at any moment. So I want to do a quick tour through what quantum computing is and what are some implications and its applications in the near term. Okay, so the first part of this, introduction is I want to convince to you that quantum computing is tangible. It's something that we can experience in simple physics experiments and witness that this is something that we can bootstrap and build into larger computing systems. And I'm going to tackle a kind of problem that would be difficult using a conventional computer. So here's a kind of contrived task that we would want to do. All right, it's a heist. So we break into a bank vault. The bank vault has 2 gold-colored bars in it. And you know beforehand that there's 2 possibilities. One is that one of them is a fake gold bar and the other is an actual gold bar. Or you could be in a bank vault where both of the bars are completely fake. And so you want to steal the gold bar, right? And if you're able to steal it, then you can forever evade law enforcement. You can fund your escape. But on the other hand, if you end up stealing a fake one, right, you'll get caught and the bar will be worth nothing. And so you don't want to risk that possibility. You're given a detector that can detect if a single gold bar is real or not. But it takes a long time to use it, so you only get to use it once. And so if this detector were purely a classical computer, then in that situation, you can only use it once, right? In general, if you wanted to fully decide if you're in either this bank vault where one is fake and one is real, or both are fake, you need to invoke the detector 2 times. And one of the first examples of where quantum computing can do something that a classical computer cannot is kind of tackling this kind of query problem, where using a quantum computer, you only need to perform 1 query as opposed to 2 queries using a classical computer to decide if which type of bank vault you're in. And this can be done using a really simple experiment. So this experiment is based off of a interferometer. So I'll paste this URL into the chat box. Okay. And so here's the kind of virtual experiment that we're going to play, right? So the setup here is we have basically 2 locations in this experiment. And in these locations, we'll put a kind of a phase shifter, something that delays a signal, indicating that, okay, this is a real gold bar, right? So your setup is either that you have both gold bars are fake. There's no additional widget that you put here indicating it's real, or you have a real one in either this location or this other location. And if you were doing a classical query, you'd have to go in and look at both of these locations, right? So you have to see, oh, gee, is this a real one or is this a real one, and so forth. So you need to do 2 queries to decide. Now, using a quantum computer, what you could do is you invoke a beam splitter, right? So we have single photon source. A beam splitter is a semi-mirrored, half-silvered mirror. It will split that beam into 2 paths. And along those 2 paths, it will see both locations and see if there's a widget there indicating that it's a real gold bar. And then you can rejoin those both paths somehow to decide if the gold bar is real or not. Right, so let's try playing that in action. Right, so I've set it up so that it'll tell you the observed and theoretical probabilities of the detector readings. So we have 2 detector here. and we can run it. So in this setup here, all of the photons, after this kind of recombination, all the detected readings go to detector 2, indicating that both are fake. And then we can put in a single phase shifter here, and we run it again. And this time around, all of the detections go to this detector here. We can also try doing it on the other side here. We'll clear the counts, run it again. And again, all the counts go to detector 1, indicating that at least one of the gold bars is real. Right? So what's the difference here between the quantum case and the classical case? In the quantum case here, we only have to do the query once. And in the classical case, we had to do it at least 2 times to fully decide whether or not there's any real gold bars in this bank vault. Right, so this is a tangible experiment. We've all played with this kind of setup in a physics laboratory. And if you look at this physical process, and instead of just viewing it as a physics experiment, but think about it as doing a kind of computation, this is already a very simple quantum algorithm. It's in fact called the Deutsche Algorithm. It was described in 1992. And it's the simplest kind of algorithm that shows that a quantum process can solve a problem in fewer queries than a purely classical one. So before I kind of move on, happy to take questions. So again, just a reminder, feel free to interrupt if there's something I can clarify. But what I'll do next is I'll do a little bit of introduction into the mathematical formalism that we use to describe these systems. Right, so quantum computing right now, a lot of it is described as proofs and equations. And so this would be a kind of mathematical description of the algorithm that I just described. So we start with the state. It's called the 0 state. So it's just like a binary bit 0, but here we're emphasizing that it's a quantum value. And we put it through this thing called a Hadamard gate, which puts it into a superposition, right? So this corresponds to, here we have a single beam traveling along the X direction. Traveling along the Y direction would be the counterpart to that. So that would be encoding 1. And by putting it through a beam splitter, we've now got a beam that's simultaneously traveling along the X direction and also the Y direction. So just to elaborate kind of what those symbols mean. So in quantum computing, we follow the binary abstraction as we did in classical computing, 0s and 1s. And in quantum computing, we emphasize, 0 states, they're really just a vector. All the vector value is concentrated in the first position. And the 1 value, binary 1, would be a vector where all the values are concentrated in the lower position. So here we go, the 0 and 1 formalism. And the beam splitter that I showed you, this would be modeled in mathematics using a Hadamard gate. And a Hadamard gate, gates in quantum computing are operations that you perform on states. And a Hadamard is a 2x2 matrix. And what quantum computing is, the way we model it is we take operations modeled as matrices, and we multiply against the vectors that describe the states. So after this, so suppose that we put the Hadamard onto 0, where 0 is a photon traveling in the X direction. We multiply it against the Hadamard matrix, and we get a state that looks like this. And here we've got a state that's in superposition. So what this describes is a state that's both simultaneously 0 and 1, and they have equal probability amplitude. Right? So these coefficients are amplitudes. In general, they're complex numbers that describe how much 0-ness there is and how much 1-ness there is. What's tricky about these probability amplitudes is they can be positive valued, they can even be negative valued, for example, here. And in fact, they can also be complex valued. And so here's a kind of full description of that. Right? So I talked about how we have 0 and 1 states, they're really just vectors. The constraints on the coefficients are such that all the probability amplitudes, all the possibilities have to still sum up to unity. And the real world probability comes from squaring the amplitudes. A lot of physical processes and phenomena can be used to encode these quantum bits or qubits. So this includes polarization of light, electron spins, the energy levels of ions and atoms. And also we can have nonlinear resonators in electronic circuits that would lead to quantized voltage and current, which can also be used to encode quantum bits. And so here we go, right? So we've described the experiment that we had before. We've taken 0 state, put it through a Hadamard, put it into superposition. And then what we have next is a bunch of possibilities. So here, this section here describes what's the setup, right? So what is the environment? What's the number of real gold bars in this bank vault? And so depending on whatever the bank vault setup is, there will be either a phase shift or no phase shift in the light paths, inducing phase shifts on the state. We can then take another beam splitter, rejoin the 2 paths back together, applying a Hadamard gate on them. And so after that, it's going to be deterministically either 0 or 1. And the 0 or 1 tells you which type of bank vault you're in. Right, so all of this we count as one query. So in one query of the system, we're able to decide, is this bank vault, does it have 1 gold bar or no gold bars at all? All right, so any questions so far? So what's tricky about that is in this kind of setup, we've also used another important property of quantum computing, which is, well, when you have amplitudes that are positive and negative valued, when you sum states by applying gates, these amplitudes can come together in constructive interference, or they come together in destructive interference. So this is how you go from a superposition state, and once you put it through another Hadamard gate, another beam splitter, they can come together and become deterministic again, right? So deterministically either 0 or deterministically 1. So these properties, right? These properties of having superpositions, states being simultaneously different possibilities, and having the probability amplitudes of those states being positive and negative valued, this can lead to interference. These key properties are part of what drives why quantum computing is fundamentally different from purely classical computing. All right, so again, I'll be happy to take questions here before moving on. So what we'll do next is we'll talk about, so I've shown you a really simple process that is in some sense quite familiar, but can also be a kind of computational process. And we kind of push out that possibility. So in really large, complicated setups, what types of problems do we think quantum computing can tackle? And what realistically will we be able to do in the relatively near term? Right? So this is some of the famous kind of implications of quantum computing. Quantum computing will break crypto systems, for example, is one such claim. And I'll counterbalance that with what's the reality of what types of systems we will have in the near term, and what might we use quantum computers for. So first, let's talk about in the far future, suppose that quantum computing works, what's the implications? So one implication of really reliable, far future, large-scale quantum computers is it changes our understanding of what types of problems computing can tackle, right? And so one such type of problem belongs to factoring, which itself belongs to kind of a set of other problems as well. And what's interesting about factoring is we use factoring as a kind of one-way function important for cryptography. And a one-way function is something where computing the process in one direction is easy, but reversing it is quite hard. Right? So multiplying two numbers is easy. We can do so in polynomial time. It takes b squared number of operations to multiply two b-bit numbers. But our understanding of how to best factor them using algorithms, our best understanding of factoring, it still requires an exponential number of operations as you grow the number of bits linearly, right? So for a b-bit number, you need 2 to the power of some power of b to reverse the multiplication, to factor it back into its components. And so we think, right, multiplying large primes is a one-way function in classical computing. But in general, we actually don't know of anything that is truly provably a one-way function. So all of this cryptography that's based on one-way functions is in some sense a little bit shaky ground. And it's even more shaky ground if you consider, well, in 1994, Peter Shor, professor at MIT, discovered that if you can build a large-scale reliable quantum computer, then that quantum computer can factor a b-bit number in polynomial time. Right? So in this setting, not only is the quantum computer able to do something that a classical computer cannot, and in fact does it in exponentially faster time. And so this is quite shocking. And this has implications on a lot of crypto systems that ultimately based on factoring numbers or a kind of variation on factoring numbers. So for example, suppose you had a crypto system based on 512-bit integers. Such a crypto system would require thousands of years using a classical computer to crack. And as you double the number of bits, this becomes exponentially difficult, right? So this is trillions or quadrillions of years to crack it. But if the task of factoring numbers is only polynomial difficulty, is O of some polynomial function of b, and factoring this number, factoring 512-bit crypto system is a matter of hours, and doubling the number of bits doesn't really buy you much more security either. So it would take a little bit more than a day, right? So these estimates come from Mark Oskin at UW in this paper here. And so a lot of problems actually all rely on factoring. So here I'm talking about a little bit hint into how this famous Shor's factoring algorithm works, right? So if you wanted to know how this factoring algorithm works, well, first we would talk about how factoring itself breaks down to a lot of other related problems. So you would take a factoring problem, you would show that, well, factoring is really just a kind of modular square root, taking the square root of numbers in modular space, mathematical space, which is itself a kind of discrete log. And that also is just like finding the period of a function, right? So you have a periodic function that repeats after some period p. Tell me what is the p such that the function repeats itself. And what's interesting is this discrete log problem is in some sense even more fundamental to crypto systems than factoring, right? So Diffie-Hellman is based off discrete logs. And this core primitive of quantum computers being able to tackle the period finding problem implies that all of these crypto systems based off of discrete logarithms, based off factoring, are vulnerable to quantum computing. And so what's the implication of this, right? So the implication of this is, well, one beneficial thing that has come from this is people realize that, it's not good that we base crypto systems off of candidate one-way functions, such as factoring, where we don't really know if it's truly difficult to reverse. And so that's goaded cryptography researchers to come up with new crypto systems that are based off of other mathematical primitives. So there's new crypto systems on the horizon, which should be even stronger than ones based off of factoring, because they are based off of mathematical primitives like elliptic curves or lattices that we know are more difficult than factoring. So is this something that we have to worry in the near term? So let's think about that. So what I have here is a kind of plot that summarizes a lot about what's the status of quantum computing right now, right? So this plot has on one axis the number of qubits that we have in a quantum computer. So this is how many bits of quantum information a quantum computer has access to. So as you see here, the quantum computers that we have today, the prototype computers that we have today have on the order of 100, maybe 200 qubits available. An equally important dimension to characterize these systems is on the x-axis here. So on the x-axis, I have the probability that an operation goes wrong. Right? So on the very far right here, I have very reliable, almost perfectly reliable quantum computers. And then on the very far left here, I have quantum computers that are completely inaccurate. Right? Every operation you perform has a high probability of it failing. And the systems today, right now, we have on the order of 0.1% accuracy, maybe 0.01 depending on the system. And so that kind of forms a Pareto curve of trading off the number of qubits that you have versus how reliable they are. And this is still a pretty accurate characterization of the systems that we have today. Maybe we've advanced a little farther than this frontier since this paper came out. So on this plot, let's go right to Shor's algorithm. So Shor's is this hashed blob here, this ellipse here, with the teal colored hashing. And to run Shor's algorithm for factoring numbers to break crypto systems, you would need to have quantum computers that's on the order of tens of millions of qubits that are all much more reliable than the ones we have right now. Right, so this is a far future kind of prospect. So all of these algorithms that are on the upper right here are all far future quantum computers, which would have much more qubits and much reliable operations that can also do an important task called error correction, where even if the quantum computer makes mistakes, there are protocols to kind of fix those errors in the same way that we have error correction codes in modern storage. All right, so let's look at some other points on this plot here, right? So one more point is we've got this frontier here, which is labeled classical simulation. And so what this is saying is using a classical computer, we can simulate quantum computers doing stuff up to this horizon, right? So a classical computer, if it's able to simulate what the quantum computer is doing, then the quantum computer is not really doing anything interesting, right? It's not more capable than a classical supercomputer or a classical simulation. And so the trade-off here is, well, if the operations are quite noisy, if the quantum operations are quite unreliable, then it's very easy to simulate them using a classical computer. A classical computer can draw distributions in the same way that the quantum computer is trying to create an interesting distribution because the quantum computer is quite noisy. And so if the quantum computer is noisy, then the existing classical computers that we have can simulate those systems pretty easily, millions of qubits. On the other hand, if you're trying to simulate a quantum computer that's quite reliable on the right-hand side here, then it becomes really hard, right? So at best, we can simulate using a classical computer, we can simulate quantum computers up to on the order of maybe 50, 100 qubits. And so this forms a frontier of where classical computing can simulate what's a quantum computer doing. Just beyond that frontier, we have a shaded area here called quantum supremacy, quantum advantage, which is a point that many teams are trying to demonstrate that they're in, where a quantum computer is doing something a classical computer cannot. Just a little farther from that horizon is a set of algorithms called Misq algorithms. So Misq stands for noisy intermediate scale quantum, where the quantum computers are just reliable and just capacious enough that it's doing something useful. So let's talk about that next. Right? So quantum computers on the verge of doing interesting and useful tasks. So up to this point, is there anything I can help to kind of clarify anything we've talked about so far?
That was a really good graph. It explains the whole problem.
Yeah, I use that graph all the time. It summarizes a lot about what's going on in the current status.
How fast are the extra bits being increased?
Let's fast forward, right? So I think that's, I kind of debated if I want to talk about that now, but yeah, let's talk about that now. So how quickly are we on this trajectory here? So this is a summary from this book published by National Academies Press. It's called Quantum Computing, Progress and Prospects. This was in 2019. They hosted a panel of 100 researchers working in various areas of quantum computing to develop a kind of consensus report on the current status of the research field. And so this plot here summarizes a bunch of papers on how far the technologies are along. And as you see, it's already pretty outdated. And so here, what it's showing is, as time progresses, more types of technologies have come online. So initially, a lot of these technologies were based on trapped ions. Superconducting based qubits came a little bit later. And further, within the same technology category, the colors indicate that as time progresses, they've become more and more reliable. Right? So controlling for the technology and reliability, this is starting to grow. Some say this is a kind of exponential growth. That's debatable. I think that's an optimistic view, but certainly it's encouraging, right? Some people like to put alongside to this graph a bold prediction from Gordon Moore of Intel, just kind of chaining together some few data points spanning, less than a decade, and then trying to make exponential projections from there, which then ended up holding for more than a few decades and ended up being a kind of self-realizing prophecy. Right, so this is kind of the viewpoint of, well, how quickly is this technology developing? Good question.
Thank you.
Yep.
Hi, this is Brian. I have some questions about the, as opposed to the theoretical, the practical issues in getting these machines working. I remember back, for example, to when the Cray, it took a whole building to house a Cray computer. And if these quantum computers require superconducting or or supercooling, the relatively impractical for the home or for the average office. And I'm just wondering when it's going to reach the point that they're mechanically practical to put into offices, although they may never be because of the types of algorithms that they're used for. Can you clarify that a bit?
Yeah, so in some sense, the physical space that they occupy is not so important. Is kind of the first thought, right? Because ultimately all these are going to be network accessed, specialized computer hardware, specialized supercomputers that, is not something that even corporations would be housing on premise. And so in some sense, the physical size is not so important. A lot of the size comes from, as you say, right? So refrigeration, the kind of physical cooling of the core components. And there's a kind of distinction between superconducting based systems versus trapped ion systems, right? So superconducting systems, they do require cryogenic temperatures. Trapped ion systems, mainly they require high vacuum. And right now, the trapped ion setups, they're housed in physics laboratories, right? They have a lot of different disparate technologies that you have to integrate together to build a trapped ion computer. You need to have the vacuum apparatus. You need to have the readout optics, CCD, camera-based op readout. You also need a laser setup to kind of drive the ions. And all of these technologies end up making the setup quite big. But there are people who are trying to kind of compactify that, right? So trying to realize a kind of trapped ion quantum computer in a desktop sized box is actually something that people are trying to integrate right now. And then a kind of third point here is that this plot is also kind of not seeing the broader perspective. Trapped ions and superconducting qubits are really just two candidate technologies. And there are other technologies based off of other solid state systems and atomic systems that might still be the actual, what ends up being the CMOS of quantum computing. We don't know what will be realized yet. I actually tell people that it's really remarkable that between superconducting and trapped ion technologies, it's actually pretty big coincidence that the two are at this relatively same technology maturity as they are now. It's kind of a very strange coincidence that they're not, orders of magnitude apart. That's a kind of another curious thing.
So I have a question, if I may.
Mm-hmm.
So one of the projections that we have today for quantum computing is that the results, the arithmetic results, are not completely accurate. You could have some results accurate, but you could have some off. I recall back when I was working in building processors for mainframes, we built a square root operator in the CMOS, and it was really fast, and it would beat any speed that the operating system or utility that would calculate the Newton-Raphson iterations, and it would provide a much more accurate number. But we had to drop it because of the fact that the results were more than 1 bit in the least significant digit off, and that wouldn't be acceptable for banks and for businesses. So that brings up another a big question. And like I think what you said very well. I think we're going to end up with hybrid systems where we're still going to be using CMOS, but for some computations, we're going to be using quantum. What's your view on that?
So this is part of a broader picture of, right, there's a lot of computing technology candidates, which are also not 100% reliable or precise or error corrected in the same way that existing digital computers are, right? Nobody would say that an analog-based neuromorphic network would be perfectly reliable, but if it models a kind of neuromorphic neuron-based model akin to something that biology does to do pattern recognition, and could do that much better than software running on digital hardware, well, then that has interesting use cases for that specific domain. And quantum computers are the same idea, right? They're not going to be general purpose at all. They're going to be used for tackling really specific problem kernels that you can offload to that quantum computer, right? It's the same way that people use GPUs or FPGAs, other specialized hardware, to offload very specific kernels of problems to be accelerated in some other piece of hardware, which is reliable or unreliable, but is fundamentally different.
Thank you.
So yeah, we can say more about how do we use unreliable quantum computers? And so researchers think that the first interesting use cases of using quantum computers will be in this kind of conjunction, right? This kind of collaboration between a quantum computer and a classical computer. Right? The basic idea is you have your quantum computer evaluating some function. We would take measurements, observe what the quantum state is, and using that observation, we calculate some kind of objective function. And we use an optimizer. So we use an optimizer running in a classical computer to come up with new parameters that parameterize the quantum hardware to calculate new values for the function. And we would do this iteratively, right? So we run this as a kind of a optimization loop. We draw many samples from the quantum hardware to kind of smooth over measurement and other types of errors. And we use optimization to as a kind of a combined calibration routine to try using the quantum hardware. And this has a lot of useful benefits, right? So in one key idea is, well, here we're using the quantum computer and the classical computer. We're drawing on the strengths of both to do computation. And so even without error correction in the near term, we could still use this to provide meaningful results. Another advantage is that because we're going to run the quantum computer thousands of times, millions of times as part of the whole algorithm, we're not required to perform many operations on each qubit. Right? So the qubit states are not long-lived. They are constantly trying to decay away. And so this addresses a kind of challenge, which is we don't have a lot of time to cram in the operations that we want to do on the quantum states. And another key strength is that we have really nice optimizer algorithms on classical computers, and using that will kind of accentuate the strengths of quantum computing. So there's a couple examples of this that we'll talk about. So these Misq near-term algorithms that combine quantum and classical, there's a couple key examples, right? So I want to give a quick overview of both. But I think in the interest of time, I'll kind of skip to kind of a, let's see. In the interest of the time, I think it's better to cover one or the other. So maybe I'll take a poll. Which one sounds more interesting, optimization or simulating quantum mechanics?
2, simulating quantum mechanics.
Yeah,
Okay,
number
seems-
2.
Number 2, all right, so let's go to number 2, sounds more interesting. So we'll skip to that. So the idea here is, we want to simulate quantum mechanics, which is, a difficult task. We'll talk about why it's a difficult task and why we can use a quantum computer as kind of a physical analogy, an analog to the quantum system to compute properties from it. So some motivating ideas. Studying quantum chemistry is a useful problem. Kind of motivating problem here is, well, one of the most important industrial processes is we need to take nitrogen gas, molecular nitrogen from the air, and turn it into something that's available for industry, typically in the form of ammonia. And the way we do that now is via the Haber-Bosch process. This is very energy intensive. It requires high temperatures. And by some estimates, this uses up 2% of the world's energy production in order to obtain ammonia to make fertilizer and other materials. And that's very perplexing because in plants they have this protein, nitrogenase, which can fix nitrogen from thin air at room temperature and do so very efficiently. And the key reason that plants can do this is because of a catalyst, iron molybdenum cofactor. And the core component of this catalyst, if we wanted to simulate it, well, we need to somehow simulate 60 electrons in 110 different spin orbitals. And this makes it an extremely difficult problem, right? So we cannot study how this works from first principles. There's other settings where quantum mechanical processes are controlling why some physical phenomena happen. So for example, high temperature superconductors. In those settings, we would want to model that superconducting behavior using these models called Hubbard models, which would tell us about a little bit why and predict what types of materials would be candidates for higher temperature superconductors. And modeling and understanding these systems are super hard. Why? Well, they're difficult because these systems are all described using the Schrodinger equation for quantum mechanics. And these Schrodinger equations, they're fundamentally PDEs. And the PDE on the right-hand side here, the function upon the present state is controlled by this matrix called a Hamiltonian, which dictates the dynamics of the quantum system. And so if we were to study a molecule, for example, we want to study a molecule, hydrogen molecule consisting of 2 hydrogen atoms, for example, we would want to write down its Hamiltonian, which says something about where the energy and how much energy is in this molecular system of two hydrogen atoms, right? And the terms or the components of this description would be captured in this whole Hamiltonian, and it has 5 components, right? So these 5 components, some of them are kinetic energy, some of them are potential energy. The kinetic energy terms say, the nuclei and the electrons are moving around. And potential energy terms say electrons are attracted to nuclei, and nuclei repel nuclei, electrons repel electrons. And so the whole equation comes down to this form here. And we would want to study this Hamiltonian, right? But unfortunately, if the molecule has more than a few atoms, right? Well, not just more than a few atoms, but more than a few electrons, maybe just more than 3 or 4 or 6, this Hamiltonian becomes extremely high dimensional. It becomes a very large dimension matrix with many elements in the matrix, which is unfortunate because being able to study this Hamiltonian, studying this matrix tells us a lot of properties about molecules. So for example, if we were able to construct the Hamiltonian of a molecule and determine what are its eigenvalues, then we can know what's the energy state of that configuration of the molecule, which would tell us if that's favorable or tell us something about the shape of the molecules. Right? So one classic example of this study is, well, on the right-hand side here, we have studying the dissociation curve of a hydrogen molecule. We're plotting the energy in the molecular configuration versus the geometry of the molecule in terms of how far apart the atoms are, right? So if the two atoms are too close together, the nuclear repulsion between the two atoms makes it an unfavorable energy configuration. And if it's too far apart, then the electron nuclear attraction also makes that an unfavorable configuration. There's a very optimal bonding distance between the two atoms where the total energy is minimized. And in order to calculate what's the energy of each of these configurations, this comes down to finding the eigenvalues of the Hamiltonian describing that molecule. Right? And we're only able to do this for really small molecules, right? So 6, 10, 12 electrons and no more. All right, so here we're able to do this exactly for hydrogen because it only has 2 electrons. And so we talked about how this is a challenging problem, right? So it's a challenging problem because, well, molecules has n electrons. The n electrons are interacting with all the other n-1 electrons, so it becomes a n-body simulation. And using a classical computer, well, a classical computer would use an exponential number of bits to represent the states as you increase the number of electrons, right? So if n is the number of electrons, then what classical algorithms are doing is they're representing the state as a exponential function of n number of bits to represent the state. In a quantum computer, it kind of reverses that, right? So instead of requiring an exponential number of bits of information, we only need a polynomial number of qubits to represent those electrons. In some sense, we're constructing a kind of analogy between the physical system and the quantum computer to use the quantum computer to model the overall system, overall quantum system. And so this goes through several stages of mapping, right? So the full algorithm of how to do this is we would follow various processes of simplifying this Hamiltonian. We make various approximations, right? So we would make one approximation that, for example, says, well, the nuclei are really heavy, so we can get rid of the terms that involve just nuclei because that has a longer time scale. That's one approximation. And another approximation is, well, we would look at the electrons and say, well, these electrons, instead of kind of writing them out, describing where they are in real space in terms of vectors of where the electrons are as a point in space, we already know that they belong in orbitals. And so we can model the molecular system in terms of orbital occupancy. That's another approximation. So 2 approximations. And the third mapping here is we would then map the orbitals into qubits, where qubit 1 means the orbital is occupied, qubit 0 means the orbital is vacant, and we can create a quantum algorithm that fully models this Hamiltonian. So if we were to able to demonstrate that kind of simulation, then this is a projection of as you increase the number of qubits that you have under control in your quantum computer, what types of molecules we would be able to simulate. So this quickly, right now, classical computing, at best, we can simulate maybe 60 electrons in the very most advanced simulations. With 100 qubits, we're already beyond those simulations. And very quickly, we start to encounter interesting systems that would, for example, if you were able to fully describe the dynamics of a protein, for example, right, we can actually, it starts to get into the territory of designing drug molecules to plug into specific active sites to change the behavior of proteins. So this is the idea of, well, in the near term, even with relatively small scale and unreliable quantum computers, hundreds, 200 qubits, not all of them reliable, that starts to allow us to do interesting problems in simulating quantum chemistry, quantum physics. Any questions up to this point? Okay, so what I'll do next very quickly is, well, we talked about how this is an interesting juncture for studying quantum computing, right? So we've talked about the principles of how quantum computing works. We talked about kind of speculative far future implications of quantum computing, how it changes our understanding of what's computable. And we talked about how there are some near-term applications of quantum computers in very specific areas like simulating processes. And this is a particularly interesting juncture to study this because quantum prototype systems are getting more and more reliable and capacious as we speak. And so one task that we need to do now is study quantum computer engineering or quantum computer systems, which is we need to fill out all the layers and components that we've built up for the computers that we have today. Compilers, languages, ISAs, microarchitectures to make this a usable overall system, right? So right now we have algorithms and we have qubits. In the middle, we need to fill out these layers. So some of the work I've been doing is in the area of simulators and programming language representations. And so in some recent work, what I've done is, right, so we want to build simulators for quantum computers because we want to study them, we want to validate results, we want to design algorithms and so forth. And one particular thing that we want to do is we want to study these Misq algorithms that I just talked about, right? So these algorithms that are based off of using quantum and classical computers in conjunction. These algorithms have interesting properties, right? So we want to tackle those interesting traits of those algorithms. So some of these traits include, one of the key things is you would take the quantum algorithm and run it thousands of times, right? So you would take a same quantum circuit, the same quantum algorithm. Its structure is always the same, but every time you run it, you change the parameters ever so slightly. And so we want to build a simulator that's able to tackle that kind of unique trait. And one area where people have done already exactly that, right? So this idea of you have a network or a circuit that has a very specific shape, only the parameters are changing. People have researched this type of problem before. So this originates in an area in AI in the form of Bayesian networks, where for decades, people have built up these systems, knowledge systems, belief networks, and so forth, where our beliefs or our models of probabilistic events about the world, we can represent them in these pictures, which capture a kind of causal relationship between events, right? So this is a prototypical Bayesian network. It says, well, for example, here, whether or not your sprinkler turns on depends on, for example, whether or not it's raining. If it is raining, then the sprinkler is not likely to turn on. It's not likely on. But if it's not raining, then the sensor will detect that and it's more likely to turn on. Right? So this kind of causal relationship of how probabilistic events affect other probabilistic events, they're encoded in these networks. And one common thing that people who use these networks have done before is you have this network, it has a fixed structure, but the parameters may change. And so if you change the parameters, you want to have something that allows you to query this network by changing only the parameters and do repeated queries. And what we did was the same observation. We have Misq algorithms that do exactly this. You have a quantum circuit, has a fixed structure, only parameters change. Could we leverage the compilation and repeated queries ideas for classical AI, for classical Bayesian networks, and use that to do the same for quantum networks, for quantum circuits? And we do exactly that. And along the way, there's some interesting transformations. So here, for example, is a first description of a quantum algorithm with noise as a kind of graphical model, using the graphical model to describe noise. And this has a lot of advantages, right? So in this viewpoint here, a lot of types of correlated noise or biased noise is actually very easy to model. And this is a kind of unique property of this approach to doing this modeling. There's some other interesting transformations too, right? So another interesting transformation is you can take these graphical models and we can actually turn them into purely logical formulas, purely Boolean-based representations. And this has the advantage that in this representation, you can actually use satisfiability solvers from computer science to crunch down these representations. And this is also kind of the first demonstration of using SAT solvers as a way to compile and manipulate quantum programs. And so another key result is, well, even with all these compilations and transformations, the semantics of the quantum circuits are the same. And we can use these ideas to build useful simulators for quantum computers and use that to study larger quantum programs and so forth. So that's kind of a high-level summary of a recent publication that we made exploring this topic, right? So here, it shows that this was work that I was doing during my postdoc at Princeton University. Professor Martinosi very recently spoke here at the chapter, and this was published at a venue called AskPlus just this year, kind of showcasing these interesting transformations. In the time I kind of have left, because I do want to end early enough to take some questions, I want to highlight kind of what's going on at Rutgers in terms of quantum computing education, right? So at Rutgers, we're building out a kind of full sequence of quantum courses, starting with quantum algorithms and also quantum error correction. My class specifically is a class called Quantum Computing, Programs and Systems, where we emphasize the quantum systems and quantum computer engineering aspects of quantum computing. And we also have classes offered in physics, which discusses how physical devices are going to implement quantum computers. So my class specifically focuses on the systems and computer engineering aspects, the compilers, the representations, the programming languages, the architectures for quantum computing. And more broadly, we also have a kind of full slate of research that's going on at Rutgers. So including Professor Szegedi, who is a mathematician doing work in complexity theory and quantum algorithms. My work is in programming languages and simulation. We also have Professor Eddie Zhang. Her work is in circuit compilation. We also have Professor Sojanen, who is a information theorist, communication theory theorist, who also studies quantum communications. And in the physics department, we have a full slate of professors and faculty and students who are researching quantum devices just as well. So with that, I'll kind of end up and wrap up my talk portion. And thanks again for the invitation, and happy to take questions about any part of it.